Hello students, today we are starting up with a new topic that is about the columns that are subjected to uniaxial bending. So we are talking about columns subjected to uniaxial bending. I have already told you the difference between the different types of columns. To further clarify it, let's basically talk about the three types of columns. See, when we have a building, some beams and columns are there to support. So we have these columns at various locations. Now typically the columns that are in the central locations, these A and A, these columns are considered to be subjected to axial compression. But these columns that are marked as B, they are subjected to bending also along with the load. See why it is subjected to bending? If we are taking about this column is taking the load from this beam and it is taking the load from this beam. Due to this, it will have some force and along with that it will have some moment. Now the moment from the opposite sides, they cancel each other. We do not have a moment along y-axis for this particular column, but this beam is going to transfer a load and a moment. So this moment is not getting cancelled from any moment from this side. So this particular column will be subjected to a load and a moment. Is it okay? So this is a column that is subjected to load and a uniaxial bending. This column, they are all subjected to similar kind of bendings. Similarly, we have these columns, they are also subjected to uniaxial bending, but now the bending will be in this particular direction. And what about these columns? These columns are the columns that are subjected to biaxial bending. They are subjected to bending from x-axis as well as bending from y-axis. So we will be dealing with this type of columns in the next classes, but now we are basically concentrating on the design of B and C type of columns. Okay? Now, the behavior of such columns will if I draw this column, it is nothing like at the CG, it will have load and it will have a moment. Or instead of saying this, we can even say this, it is subjected to a load. If this is the CG, it is subjected to a load at certain eccentricity, where moment is equal to P into eccentricity. Ultimate moment is equal to PU into E. So behavior of this kind of column will depend upon the magnitude of P and magnitude of moment. Or we can say it depends upon the ratio of MU upon PU, that is E, eccentricity. So we can say that the behavior of column will depend upon value of eccentricity. Okay? Based on that, we have four cases in which the column is going to behave. The case number 1 is axial loading case. Axial loading case where eccentricity is 0. Case number 2 is when eccentricity is small. Case number 3 will be there is eccentricity is large, and case number 4 is eccentricity is very large. So why I am dividing this into 4 categories is because behavior of each type of column is different. So let's discuss the behavior of each column based on the eccentricity. So I am talking about the first case. First case is case 1. Case 1, that is column is subjected to axial loading. There is no moment. So it means if I am having this column, this is the cross-sectional area of the column, This is width of the column, this is depth of the column, overall depth of the column. This is the central location CG of the column. And the load is acting right at the CG of the column. So load is acting right here at the top of it. Okay. Now due to this, you can all understand that if this is a member, now I am drawing the front view. This is the member. Load is acting here. It is a compression member. Whole of the member will be under compression. So compressive strain will be same. So I am drawing the cross section. I am drawing the compressive strain on the member. So compressive strain distribution will be all compressive. And because we know from one of the clauses that is given in the code that the maximum strain in concrete in axial compression is taken as 0.002. We will consider that the column has failed when the maximum axial strain in concrete has reached 0.002. So I am taking the critical case. So what we will say is the maximum strain value is 0.002. And if you all remember, due to this strain, the stress distribution diagram for 0.002 strain, the stress distribution is 0.446 FCK. Is it okay? So the stress distribution is 0.446 FCK. So what we are saying is, so corresponding to this, the stress distribution it is all compressive and the maximum value is 0.446 FCK. Is it okay? And what about the neutral axis? Neutral axis is the point where compression and compression gets changed into tension, and we have a zero net compression or net tension is zero. So we can say that the neutral axis lies at infinity. In this case, that is infinity, because whole of the thing is compressive, so there is no neutral axis in this. The neutral axis must be lying in the infinity region. Okay. Now coming to the second case, case 2. It says neutral axis lies outside the section. Eccentricity is small. So this is the case in which you are having, I am drawing the front view now, you are having a column in which load is not acting at the CG, rather load is acting at a small distance with the eccentricity E. If I draw the cross section of this column will be some width B, some depth D. This is the neutral axis, this is the CG. Now the load is acting here. Load is acting at certain eccentricity E. Is it okay? Now due to this, what will happen? There will be stresses due to the load, and there will be the stresses due to the moment generated. So if I draw the stresses due to the load and the moment generated, so stresses due to this load P, it will be all compressive, and stresses due to moment generated, just consider that just like a beam, it will be compressive in certain location, and then it will be zero somewhere here, and then it will be tensile in other location. So it is compressive and it is away from the section, that is tensile. So this side is tensile, this side is compressive. So what will be the net stresses on a cross section? Net stresses on the, first of all, net strains on the cross section. Net strains on the cross section. There will be compressive strain due to this. There will be compressive strain due to this. So net strain on this edge will be addition of these two compressive strains. There will be net compressive strain due to this on this end. but a tensile strain on this. So net compressive minus tensile, there will be some strain on this edge. Because we are considering eccentricity is small, moment formed will be small, tensile strain will be small. So net strain on this side, C minus T, will have C output. So net strain on this side will be compressive. So we are talking about this particular case. This is the strain distribution. On this side we have maximum strain. On this side we have minimum strain. Is it okay? And we will have a strain value of 0.002. Up to that strain value, what we expect is the system will have stress distribution that will be rectangular. Because after 0.002 value, there will be value greater than 0.002, and for that we know the concrete gives us the rectangular stress distribution. And below this, below the strains of 0.002, what we will have? We will have a parabolic distribution. Now we will not have zero of this particular parabola anywhere in the column because whole of this is under compression. There is no zero strain, there is no tensile strain. So what does it mean? Your neutral axis or the point of the parabola will lie outside the section. So this is the neutral axis. So neutral axis is lying outside the section. So this is the stress distribution. This is the strain distribution. This is the minimum strain, and this is what? This is the minimum stress that is coming. And whole of the system is subjected to compressive stresses, where maximum stress is 0.446 FCK. Minimum stress is some value, but the minimum stress is not zero because we have a compressive strain here. So it means the tip of this particular parabola will lie outside the section, and that is what the second case is. Neutral axis lies outside the section. Okay. Now for this we have in the clause that is given limit state of collapse for compression, point number B. See, understand this. These are the assumptions. The maximum compressive strain at the highly compressed extreme fiber in concrete subjected to axial compression and bending. So it means they are talking about uniaxial bending case, and when there is no tension on the section. See, this is the section, there is no tension anywhere. This is the section, there is no tension anywhere in the section. Whole of this is compressive strain. So this is compressive this side, on this side also this is compressive. So in this case they are saying shall be 0.0035 minus 0.75 times the strain at least compressed extreme fiber. So what does the code says? As per clause 38.1, point B, it says epsilon maximum must be equal to 0.0035 minus 0.75 times epsilon minimum. This is the relationship between the maximum compressive strain, minimum value, and the maximum value. Okay. So this is, I am talking about the third case. Neutral axis, the eccentricity is very small. So due to this small eccentricity, there will be compression throughout the section. But now the compressive strain is not uniformly distributed as it was there in case 1. It is distributed with some maximum strain on one end and minimum strain on the other end. Okay. Now coming to the third case, case 3. Case 3 is eccentricity is large. Now eccentricity is large is of such value that and is of such value that neutral axis lie along the edge. Now what do I mean? If I am talking about the front view, this is the column. Now load is not acting at the CG, load is acting at some eccentricity E. So it means ultimately what are we having? We are having a combination of P and moment. This P is going to give me the compressive strain due to P, and this moment is going to give me the compressive strain on one edge and the tensile strain on the other edge. Now eccentricity is such that this compressive strain is equal to the tensile strain on this side, so net strain on this side will be 0. So if I am trying to draw the cross section, the cross sectional parameters will be B and capital D. B by D is the cross section of the column. The strain distribution, because on this edge both the compressive and tensile strains, they are equal, they cancel out each other, net strain is 0. And net strain on this particular side will be compressive, they will add up. So net strain on this particular side is some E epsilon. And the code says in such case the maximum strain can be 0.0035. So this is the strain distribution. Correspondingly, the stress distribution will be at the point where the strain is 0.002. Up till this point the system will have a rectangular distribution. Beyond that, this particular system is going to have the parabolic distribution. Now what we will have the point, the origin of the parabola right within the cross section, because the origin of this particular strain is at the edge. Okay, so in this case your XU becomes equal to depth, that is neutral axis will be equal to the depth. Okay, clear? We all know this particular value will be 3 by 7D and this particular value will be 4 by 7D from the basics of this particular equation. Is it okay? So this is case 3. Now coming to case 4. Case 4 is neutral axis lies within the section. Lies within the section. Now what does this case say? Again I am drawing the front view. This is the front view of the column. The load is not acting at the CG, but load is acting at some eccentricity. Due to this, we all know there will be a combination of P and M. Okay? Because of P, there will be compressive strain. Compressive strain because of P. Because of M, there will be tensile strain on this side. There will be compressive strain on this side. So this is compressive on this side. This is tensile on this side, and it is due to M. Now the M value is such large that this tension value is greater than C. So this T is greater than C. So net strain on this particular side will be tensile. So net strain will be tensile. So in this case, if I am drawing the cross section is B by D. On this side, we will have compression added upon. So we will have some compressive strain. We will have on this side, instead of compressive strain, we will have tensile strain, because on this side your tensile strain is greater than compressive, so net is tensile. So if I join the strain diagram, so this strain diagram is tensile on this side, compressive on this side, your neutral axis is lying within the section. So this is the neutral axis that is lying within the section. Okay. So if I am drawing this is strain distribution. If I am drawing the stress distribution, we know the tensile zone, the concrete in the tensile zone is neglected. So we will draw the stress distribution of only compressive zone for concrete. Is it okay? Clear? This particular will be up till point 002. You will have the rectangle parabolic. After that you have a rectangular stress distribution, and the maximum compressive strain is 0.0035. So in this case, this particular XU is less than D. This is stress distribution. Now why the system is divided into 4 cases? Because failure of this kind of column will depend upon in which case the system will lie. So if I am talking about types of failure for this column. So it can be broadly divided into 3 categories. See, one is if the column is belonging to case 1. Case 1 means eccentricity is 0. The column is directly under compression. So the failure of this kind of column will be a compressive failure, and it will be due to crushing of concrete. So when will the column fail? When the concrete stresses exceed its compressive stresses, and there will be sudden crushing of concrete. Okay. So when eccentricity is 0. Case 2 was when eccentricity is small. Again, in the case of eccentricity is small, you know primarily the system was under compression only. So the type of failure will be due to crushing only. Then it is case 3 and beyond. So rather I will say case 4. Eccentricity is very large. Okay. If it is very large, you all remember this. If it is very large, it was this case, there was tension also, there was compression also. It means, if you all remember, that it is a case of just like a beam. Because in a beam, if the system was subjected to a moment, the stress distribution and the strain distribution used to be like this. There was some compressive strain, some tensile strain, and the system used to fail due to this particular in the tension zone because of the cracks occurring in concrete. So it means in this case it is just like a flexure member. The column behaves just like a flexure member, and it means the failure will be mostly by tension. So mostly by development of tensile stresses. So this is a type of failure. Now when I say analyze a column in uniaxial bending or design a column in uniaxial bending, we will have to consider which type of failure the column is actually falling into. Okay. Now in order to understand that particular thing, we must first of all understand one typical parameter that is existing in these kinds of columns, that is column interaction curve. Column interaction curve, or it is called PU-MU curve. So what is its definition? It is a graphical representation. It is a graphical representation of design strength of column under uniaxial bending for a given geometry. for a given proportions. Now what do I mean by this? Now let us say I have some column, the dimensions of column are 400 by 400. The type of steel and the amount of steel is also given. The column is under uniaxial, it is under uniaxial compression only. I think we will be able to calculate how much load the column can take. The formula we know. But if along with that uniaxial load you have a moment also, then what will happen? As the load with the increase in moment, there will be some combination of Pu and Mu that this particular column can bear. If the moment increases, the load that can come on that particular column will decrease. Okay. So, if I try to make the diagram between Pu and Mu, if there is no moment that is coming on the column for a given proportions, like given geometry, how much is B and D of the column, how much is the reinforcement that you have given in that column, I can say this is the load, that maximum load that this column can take if there is no moment. Now if I increase the moment, the value of load that this column can take will decrease. Okay. So what kind of curve that I'll get if I'll plot this particular combination of Pu and Mu? I generally get a curve of this kind. Is it okay? So this curve says if my moment value is this one, I can take, this column can take a load of this. So this is a typical combination this particular column can take for a moment and a load. Okay. Now there are some important points on this particular curve that are important to note. First is point number 1. So point number 1 indicates the maximum load the column can take when there is no moment. So it means point 1 corresponds to the point where it is pure axial load. Load that is with E equal to 0. Is it okay? But now, what does the code says? The code says even under the case of axial compression, we will consider the column to have some minimum value of eccentricity. So this point 2 is the point that corresponds to the load that it can take if there is some minimum value of moment or minimum eccentricity in the system. Is it okay? So second point is minimum eccentricity in the system as per clause 25.4. Is it okay? Clear? Now point number 3. This is point number 3, let us say. So point number 3 considers the case when there is no load, like I should not say there is no load, when the load is acting at such a large eccentricity that the moment becomes very large. So practically the effect of load becomes 0. Is it okay? So point number 3 corresponds to very large eccentricity, so that effect of M predominates. Now if there is only M, we all know the system will bend just like a doubly reinforced beam, and there will be a tensile kind of failure. Okay, so the behavior will be just like a flexure member. Behavior will be like flexure member. And failure will be tensile. Is it okay? Now if you move above this curve till this particular point, what is happening is, if I increase the load, that is I decrease the eccentricity, then the column can take some load and increased value of moment, and the point will reach up till this point. This point is corresponding to a balanced section. It is a balanced section. What do I mean by balanced section? that it is a combination in which tension and compressive strains become equal. So you remember we were talking about this particular case, case number 4. In this case we had compressive strains, we have tensile strains. If the compressive stresses and the corresponding tensile stress in steel, they reach the maximum at the same time, we call that section to be a balanced section. Is it okay? So it means point number 4 typically corresponds to a balanced section. That means the compression strain stresses in concrete becomes equal to tensile stresses in steel. Okay? So point number 4 corresponds to a balanced section. Okay? Now there is another point that is important, point number 5. Now point number 5 is, this is point number 5. So point number 5 corresponds to case 3. Case 3, what was case 3? Case 3 was when there was no tensile stresses, but at one edge there was strain was 0. Is it okay? So it is equivalent to case 3 when XU was equal to D, neutral axis was equal to D, when E is less than ED, the system will fall in case 2, system will fall in case 2, and when E is greater than ED, the system will fall in case 4. Is it okay? Now, this balance section is very important because below this balance section there is a tensile failure, just like a flexure member, and above this particular there is a compressive failure. Is it okay? So it means for a particular geometry, we know there is a combination of PU and MU, and if on that column a combination of P and M lies inside this particular envelope, we will call the column to be safe. If it lies outside this particular envelope, we will call that particular column to be not safe for that particular load. So this column interaction curve is very important. This forms the basis for the design. Now, rather than doing all those very extensive calculations, what does the code says? That we can find out the load carrying capacity and we can even design the column by using these column interaction curves. Now, how to use these column interaction curves, I am going to cover it in my next lecture. Okay? Thank you.